Next topic of application of derivative is increasing and decreasing functions. So first we discuss increasing functions. So see the definition of increasing function. A function f is said to be a monotonically or strictly increasing function on an interval open interval ab if for any x1 x2 belongs to open interval ab with if x1 less than x2 we have f of x1 less than f of x2. That means here we consider function f and consider interval open interval ab, and for that interval ab we select two elements x1 and x2 belonging to open interval ab such that x1 less than x2, and from that x1 less than x2 for function we get f of x1 less than f of x2. Then such type of functions called increasing function. So see here, consider an increasing function y equals to f of x in open interval ab. So here we consider function y which is increasing in open interval ab. So see how we write, let h greater than 0 be a small increment in x, then x less than x plus h. When we add some value in variable x, so here we consider that value as h which is greater than 0. So the value added in x which is always greater than value of x, so we write here x less than x plus h, and we denote this x as x1 and x plus h as x2. So see the graph. Here we consider open interval ab, and belonging to open interval ab we consider two value x1 and x2. So for x1 we write function f of x1, for x2 we write function f of x2. This graph is increasing, so we get the value of f of x1 at x1, value of f of x2 at x2. The value of f of x2 is greater than value of f of x1. So here we write f of x less than f of x plus h. X we denote by x1, x plus h we denote by x2. So we write here f of x1 less than f of x2. Therefore we can write this in f of x less than f of x plus h2 in this way also. F of x plus h greater than f of x, we write f of x plus h in left hand side and f of x in right hand side. So we have to change this inequality. So instead of writing less than we write greater than, because f of x plus h is greater than f of x. So we write this f of x less than f of x in this way also. Now we transfer this f of x to left hand side. So we write here f of x plus h minus f of x strictly greater than 0. Now we divide both sides by h. So in left hand side we write f of x plus h minus f of x upon h, in right hand side 0 upon h. So 0 upon any number we get 0. So we write here f of x plus h minus f of x upon h strictly greater than 0. So if we apply the limit for left hand side, which is definition of derivative, that is by using first principle, we write left hand side as f dash of x. So we write this as f of x plus h minus f of x upon h greater or equals to 0. So applying the limit, we write this left hand side as limit h tends to 0 f of x plus h minus f of x upon h, which is definition of derivative by using first principle. So we write this left hand side after applying limit h tends to 0 as f dash of x. That means f dash of x is greater or equals to 0. That means from this we say when f dash of x greater than 0, then the function is increasing. So see here, if f dash of a greater than 0, then a small delta neighborhood of a. So we consider here open interval instead of ab as a minus delta a plus delta. We have f strictly increasing if f of a plus h minus f of a upon h greater than 0 for mod of h less than delta. So here if we consider delta, that is neighborhood of a, then instead of writing a minus h a plus h, we consider here open interval a minus delta a plus delta. Now see here, hence if 0 less than h less than delta, f of a plus h minus f of a greater than 0 and f of a minus h minus f of a less than 0. Thus for 0 less than h less than delta, f of a minus h less than f of a and f of a less than f of a plus h. So see, with the example we clear the concept of increasing function. Show that the function f of x is equal to x cube plus 10x plus 7 for x belongs to R is strictly increasing. We have to show this function is increasing for all x belongs to R. So first we differentiate the given function. So write in solution, given that f of x equals to x cube plus 10x plus 7. So differentiate both sides with respect to x. So we write here simply differentiate with respect to x. Derivative of f of x, we write f dash of x. Here we find derivative of first term, derivative of second term, derivative of third term. Derivative of first term, so derivative of x cube is 3x square. Derivative of second term, that is derivative of 10x. 10 is constant but with variable x, so we keep 10 as it is. Derivative of x with respect to x is 1, so we write a derivative of 10x as 10, and 7 is single constant, so its derivative is 0. So in this way we first find f dash of x, which is 3x square plus 10. Now we have to check whether this f dash of x is greater than 0 or less than 0. But here we have to show the function is strictly increasing. That means we have to show f dash of x strictly greater than 0. So we check for the value x which is belongings to R. So first we substitute value of x as 1. Then we know that 1 square is 1, so 3 into 1 we get 3. 3 plus 10 we get 13, and we know that 13 greater than 0. We take negative value. When we substitute x equals to minus 1, then minus 1 square we get plus 1. So 3 into 1 3, 3 plus 10 we get 13, again 13 greater than 0. So this function f dash of x is greater than 0. That means we take positive value, negative value. So from this first 3x square, here square of x is given, that means for any positive or negative value of x we get the positive value, and 10 which is greater than 0, that means when we add or subtract any value from the 10, but here power of x is 2, so we get here always plus value. So f dash of x is always greater than 0. So we write here 3x square greater or equals to 0. When we get this value as 0 when x equals to 0, but here this value 10 which is greater than 0, so we write here 3x square greater or equals to 0 for all x belongs to R and 10 greater than 0. So there is one condition, when x equals to 0 we get value of this first term as 0, but when x is plus or minus, that is other than 0, we get the value of this first term is always positive. So f dash of x is greater than 0. So we write here 3x square plus 10 greater than 0. That implies f dash of x greater than 0. Therefore the function is increasing. Why we say strictly increasing? Thus f of x is strictly increasing function, because here we use strictly greater than sign, because we get the value of this function which is strictly greater than 0. Now second, decreasing function. So first we write the definition of decreasing function. Now see the definition. A function f is said to be a monotonically or strictly decreasing function on an interval, open interval ab, if for any x1 x2 belongs to open interval ab, with if x1 less than x2 we have f of x1 greater than f of x2. In increasing function we have if x1 less than x2 we have f of x1 less than f of x2. But in decreasing function, if you observe here, condition changes. If x1 less than x2 we have f of x1 greater than f of x2. So this is a definition of decreasing function. So see here, consider a decreasing function y equals to f of x in open interval ab. Let h greater than 0 be a small increment in x, then x plus h greater than x. In that case we write x less than x plus h. Just here we change the equality sign. Instead of writing less than, we use here greater than. So we write here x plus h strictly greater than x, and we denote this x as x1 and x plus h as x2. So here x2 is greater than x1. So see the graph, we get graph in this way. Here x1 is less than x2, but f of x1 is greater than f of x2. So graph we get in this way, in decreasing form. So from this we write f of x less than f of x plus h. In that case we write f of x plus h minus f of x. So here we write first this x as x1, x plus h as x2. Therefore f of x plus h less than f of x. Now we transfer this f of x to left hand side. So we get here f of x plus h minus f of x less than 0. Therefore f of x plus h minus f of x upon h less than 0. So here we divide both sides by h, and again this is a definition of first principle. For that we have to apply limit h tends to 0 on both sides. So we write here less or equals to 0. So when we apply the limit, we write this left hand side as f dash of x. So write here f dash of x less or equals to 0. If f dash of a less than 0, then in a small delta neighborhood of a, that means if derivative of a function at x equals to a is less than 0, then here for a small delta neighborhood of a, so we consider here that is a minus delta, a plus delta open interval, we have f strictly decreasing, because f of a plus h minus f of a upon h strictly less than 0 for absolute value of h less than delta. So we write here, hence for 0 less than h less than delta, f of a minus h greater than f of a greater than f of a plus h. In increasing function we get the value here f of a minus h less than f of a less than f of a plus h. In decreasing function here we get f of a minus h greater than f of a greater than f of a plus h. Now this note is important while solving the problem. Whenever f dash of x equals to 0, at that point the tangent is parallel to x axis. So we already discussed this in finding the equation of tangent and equation of normal. So in that case we find the slope of the tangent to the given curve and we differentiate the given curve. So this f dash of x is nothing but the slope of the tangent, and we know that when slope of the tangent is 0, then that tangent is parallel to x axis, because line parallel to x axis has slope 0. So we write here, whenever f dash of x equals to 0, at that point the tangent is parallel to x axis. We cannot deduce that whether f of x is increasing or decreasing at that point.